gaseous state. Okay, so for today, we will discuss the ideal gases and real gases, and we'll also discuss today the liquid state. So we'll also discuss various properties of liquids, such as the vapor pressure and the viscosity. Okay. So for today, again, so this is the gaseous state. Today, we will discuss one, the properties of gases, second, the kinetic molecular theory, third, the gas laws, ideal gases, and real gases. So guys, lahat ng about gas nandito sa ating crash course. So guys, makinig kayo, okay? Gina ba? Siyempre Gina, okay? So gases, they consist of particles that are relatively far apart. The gas particles are move about rapidly and have little effect on one another unless they collide. Oh, guys, bakit relatively far apart ang mga gases yun? Because the large spaces between the particles, they will explain bakit yung gases very low yung densities nila than liquids and gases. Diba? Kasi napaka-far apart ng mga particles ng gas. Okay? Napakarami ng empty space ng gases. That is why it is easy to compress them by applying external pressure. Diba? Nakita na natin to when we got to thermodynamics, where when we push a piston, diba? On a cylinder filled up of gas, right? It is easy to compress, right? It is easy to expand. And for the second reason, okay, it's because gases can diffuse very fast through each other. Okay, because they move rapidly, right? So it's easy for them to diffuse. Okay, that's why gas particles can form a homogeneous picture. And third, gases is expand to fill their containers. Right? They take the volume and shape of their containers, okay, because they have a very random motion. So for example, they take the shape of a balloon, right? When we inflate a balloon, okay, the balloon is made up of gas, right? It takes the shape of your balloon. Okay? And here you will see that the gas particles are very far apart. Okay? Compare mo sa ating liquid, guys, diba? They are more close to each other. The particles are closer to each other. Okay? And sa solids naman, diba, our particles are more packed. Okay? They do not move. As compared to gases, which has so many empty space, they are far apart from each other. Kaya, yung gases natin, meron silang very random motion compared to liquids and gases. Now, the gas kinetic theory relates the microscopic characteristics of the gas molecules to the macroscopic characteristics of gases. Okay? So, in reality, guys, yung kinetic molecular theory of gases, they will try their best. Ito yung model natin to see how molecular behavior works for gases. Okay? Yung goal ng kinetic molecular theory is to see what is the behavior of an ideal gas. Okay? So, guys, please watch this video first on kinetic molecular theory.
Let's start with a visualization of solids, liquids, and gases. First, solids have particles in closed fixed positions. And when solids melt into liquids, these particles have more positions available to be in. Notice, in the liquid phase, these particles are more spread out, but still close to each other. But in the gas phase, these particles are allowed to occupy any position available, as per the rules of entropy or randomness. In fact, one can think of the gas phase as mostly empty space. Keep this in mind as we discuss kinetic molecular theory. Kinetic molecular theory states that the distances between particles is so great compared with the volume of the particles that we can essentially ignore the volume of the particles and ignore the interactions or forces between particles. This is important because this means we can treat the particles as individual entities, which is one of the reasons the gas laws work. Here are the first two postulates of the kinetic molecular theory. Since the gas phase is mostly empty space, we can treat particles as a point of mass and ignore the volume and assume the volume of each particle is negligible. Second, we can ignore the interparticle forces. At ideal temperatures and pressures, the gas phase is mostly empty space, and in the rare occurrence that these particles do collide, we can assume any collisions are elastic and brief. Here's the third postulate of kinetic molecular theory. Gas particles are in constant random motion. They must be. This is why they exert pressure. Balloons and tires stay inflated. When the particles collide with the walls of the container, they exert pressure. And finally, the Kelvin temperature of the gas is directly proportional to the average kinetic energy of the gas. This gives us the meaning of temperature. Thermodynamically speaking, the average kinetic energy is equal to 3/2 RT. Recall, the ideal gas law applies to all gases behaving ideally. Similarly, notice how the average kinetic energy of a gas applies to all gases behaving ideally. Kinetic energy is only dependent on the temperature of the gas. In our next video, let's discuss how we arrive at this equation.
Ayan, so now you know the concept of kinetic molecular theory, okay? Dapat memorize natin guys sa board exam ang ating postulates. So, these are the postulates of the kinetic molecular theory, okay? So first, the absolute temperature is directly proportional to the average kinetic energy. Tama naman, di ba? Because when you increase the temperature, okay, kinetic energy of the particles increases. That's why they will move faster. The gas particles will move faster. Second, there are no attractions or repulsions between the particles, okay? So here, we neglect the attractive and repulsive forces between the gas particles, okay? We assume that the gas particles, they move independently and they do not interact with each other through attraction or repulsion, okay? Why? Because this will help us simplify calculations for an ideal gas, and they will help model gas behavior under certain conditions. Third, the volume of particles. The volume of particles is negligible to the total volume the gas occupies. Diba? Again, we treat the gas particles as point masses. That's why the volume of the particles negligible siya. Okay? Why? Because the actual size of your gas particles, diba, napakaliit niyan compared to the space between them, diba? Because gas is mostly empty space. You have big empty spaces between the gas particles. Okay? That's why we will ignore the individual volumes of your gas particles. Okay? Why do we do this, guys? Because it will allow us to treat gases as if they are made of point masses or point particles. Okay? So here we see, okay, the interactions of gas molecules, diba? They move in random motion and they have no attractions or repulsions between the particles. Okay, next. Gases are composed of rigid particles. So that is also a postulate of the kinetic molecular theory. So it states that gas particles, okay, hindi sila pwede mag-deform. Hindi sila pwede mag-change ng shape as they move or collide. Okay? We treat them as hard, solid spheres. Okay? And then another postulate, the particles are in constant motion and may collide with one another or with the walls of the container. Okay? Diba yung gas particles natin, guys, meron silang movement in random directions. Okay? So when they will collide with each other or with the walls of the container, okay, these collisions will cause pressure. Diba sabi kanina? Okay? Collisions will cause gas particles to exert pressure. That's why we are able to inflate a balloon, right? And lastly, okay, this is another important postulate. Collisions are perfectly elastic. So in an ideal gas, kapag nagko-collide ang mga particles, okay, ang meaning ng elastic collisions ay wala tayong loss of kinetic energy. Again, there is no loss of kinetic energy. Kinetic energy is being completely conserved. Diba? This means the total kinetic energy before and after the collision of gas particles, same lang. Okay? And no energy is lost as heat or sound. Okay? Yeah. So again, those were your kinetic molecular theory postulates. Okay? Guys, relevant yan sa boards. Okay? So make sure na gets ang mga various postulates. Now, let's move on to the molecular velocities of ideal gases. So these explain the behavior of our gas molecules based on the kinetic molecular theory. So these equations, guys, are only applicable to your ideal gases. Okay? So syempre guys, take note ha, pag sinabing kinetic molecular theory, applicable lang ito sa ating mga ideal gases because it shows us the ideal gas particle behavior, right? Okay. So here are the equations. So first we have root mean square velocity, and it describes the square root of the average of the squared values. Its formula is mu is equal to square root of 3RT over M. Okay? R is your universal gas constant, T is the temperature, and M is the molar mass. Okay? Next, we have the average velocity, and it shows us the mean of the velocities of all molecules. So the formula is average velocity is equal to square root of 8RT over molar mass. And lastly, most probable velocity, okay, it is the velocity at which the largest amount of gaseous molecules are moving. So the most probable velocity is equal to square root of 2RT over M. And again, M represents your molar mass, okay? I hope that's clear, guys. Again, take note of these equations, okay? Now, let's move on to, ayan. So here we will see the speed comparisons between the most probable velocity, the average velocity, and the root mean square velocity. So here we see, guys, na ang may faster speed, I see root mean square, okay? Followed by the average velocity, and with the least speed, that is your most probable velocity. Again, pinakamaliit ang most probable velocity out of the three, okay? Ayan. So guys, recall lang tayo sa ating gas laws. Diba? You have discussed this in your online bridging course. So the gas laws reflect the quantitative relationships existing among properties of gases. So ang mga laws na to follow the ideal gas conditions, meaning these only apply for ideal gases because they align with the kinetic molecular theory. So recap lang to, guys, okay? So first for the Boyle's law, the equation is P1V1 is equal to P2V2. As the volume decreases, pressure increases, and volume increases, pressure decreases. Okay? And for the Charles's law, so the equation is V1 over T1 is equal to V2 over T2. Okay? It implies that as we lower the temperature, then the volume also decreases. If we increase the temperature, then volume also increases. Okay? And lastly, we have the Avogadro's law. Okay? So the equation is V1 over N1 is equal to V2 over N2. Sabi lang dito, when we remove gas molecules, okay, for example, less number of moles, N, then the volume decreases. And if we add gas molecules, so if we increase the number of moles, then volume increases. Then we also have Gay-Lussac's law. So Gay-Lussac's law relates pressure and temperature at a constant volume. So P1 over T1 is equal to P2 over T2. And lastly, we have the combined gas law. This is very important, guys. P1 V1 over T1 is equal to P2 V2 over T2. Guys, dapat memorize ang combined gas law. Never to nawawala sa board exam. And lastly, we have the ideal gas law, that is PV is equal to nRT. Dapat naisa puso na, guys, ang mga gas laws na yan, okay? So these graphs show the Boyle's law, Charles' law, Gay-Lussac's law. Okay. So here we see Boyle's law. As volume increases, pressure decreases at constant number of moles and constant temperature. Then for Gay-Lussac's law, as pressure increases, temperature also increases at constant number of moles and volume. Lastly, for the Charles law, it shows that as temperature increases, volume also increases, right? At constant number of moles and pressure. To easily visualize our gas laws, okay? Tingnan natin ang video na ito.
Consider a gas-filled container that has a movable piston. It is exposed to an atmospheric pressure of 1 atmosphere. Click on one of the buttons to see animations of how temperature, pressure, or the number of gas particles affects the volume that the gas occupies. You can increase the pressure by adding a weight on top of the piston. Let's add a weight that will increase the pressure on the top of the piston to 2 atmospheres. As the pressure on the gas increases, the volume that the gas occupies decreases. The volume that the gas occupies will continue to decrease until the pressure of the gas equals the external pressure on the piston, which is 2 atmospheres. The volume occupied by the gas will be half its original volume. You should see that the volume is inversely proportional to the pressure. V is proportional to 1 over P. Adding a proportionality constant K, we can write volume equals K divided by pressure, or pressure times volume equals K. This relation is known as Boyle's law, which states that the volume of a fixed amount of gas is inversely proportional to the gas pressure at constant temperature. As the pressure on the gas decreases, the volume that the gas occupies increases. The volume that the gas occupies will continue to increase until the pressure of the gas is equal to the atmospheric pressure on the piston, which is 1 atmosphere. Let's use a Bunsen burner to increase the temperature of the gas. As the temperature of the gas increases, the volume that the gas occupies increases. In other words, volume is directly proportional to the temperature of the gas. We can write volume equals K times temperature, where K is a proportionality constant. This relation is known as Charles' law, which states that the volume of a fixed amount of gas is directly proportional to the gas temperature at constant pressure. Note that as the temperature is doubled at constant pressure, the volume that the gas occupies. When the Bunsen burner is removed, the temperature of the gas decreases, and the volume that the gas occupies decreases. The volume that the gas occupies will continue to decrease until the temperature of the gas equals the external temperature. Let's use a Bunsen burner to increase the temperature of the gas. As the temperature is raised, the average velocity of the gas particles increases. Thereby the frequency and intensity of collisions of gas particles with the container walls increase. Pressure, which is defined as the force exerted per unit of surface area, will clearly increase as the frequency and intensity of collisions increase. Pressure for a fixed amount of gas at constant volume is directly proportional to the temperature. Note that as temperature is doubled at constant volume, the pressure exerted by the gas doubles. When the Bunsen burner is removed, the temperature of the gas decreases. The average velocity of the gas particles decreases, thereby the frequency and intensity of collisions of gas particles with the container walls decrease. Pressure for a fixed amount of gas at constant volume is directly proportional to the temperature. Gas particles are entering the container. As the number of particles, or equivalently the moles of gas increases, the volume that the gas occupies increases. In other words, volume is directly proportional to the number of moles of gas. We can write volume equals K times N, where N is the number of moles of gas and K is a proportionality constant. This relation is known as Avogadro's law, which states that at constant pressure and temperature, the volume of the gas is directly proportional to the number of moles of the gas. In this animation, the moles of gas particles is doubled, and correspondingly the volume occupied by the gas is doubled.
Okay, guys, so now you know how we can visualize the gas laws, okay? I hope that's clear. Ayan. Now let's move on to these concepts related to ideal gas and gas mixtures. Now let's start with Graham's law of fusion. So it describes the movement of gas particles. So let's say we have two gas particles, A and B, through a small hole. So guys, when you say a fusion, movement of gas particles in a small hole. With the rates of a fusion of gas A and gas B, they are inversely proportional to the square roots of their respective molar masses. So here, okay, the rate of a fusion of A, VA, and the rate of a fusion of B, VB, that is equal to the time it takes for a gas particle B to fuse divided by the time it takes for gas particle A to fuse. And that is equal to square root of mb, that is the molar mass of gas B, divided by molar mass of gas A. And this is equal to the square root of momentum of gas B divided by the momentum of gas A. Okay. And then we have the apparent molar mass. So it is the average molar mass of a combination of gases in a gas mixture. Okay. So apparent molar mass is equal to the summation of mole fraction of the component of your gas mixture times the molar mass of component. So for example, guys, meron kayong tatlong components in your gas mixture, gas A, gas B, and gas C. Okay? You have to get their respective molar masses, okay, and multiply it to their respective mole fractions in the gas mixtures, okay? And then next we have the Dalton's law of partial pressure. So it states that the pressure exerted by an ideal gas mixture, that is PT, again, that is the pressure exerted by your mixture, it is just the sum of the partial pressures of the individual gases, which makes up your gas mixture, okay? So PT is equal to the summation of the partial pressures of the individual gases. So if you have, for example, two gas components, then we sum up the partial pressures of gas A plus partial pressure of gas B. Okay? And then we can also get the mole fraction of a component in a gas mixture that is equal to the Ni, okay, mole fraction of the gas component divided by the total number of moles. So again, total number of moles of your gas mixture, of your component of the gas mixture divided by the total number of moles. And this is equal to the partial pressure of the gas component in your gas mixture divided by the total pressure or the pressure exerted by the mixture, okay? Pi over Pt. And then next we have humidity. So it indicates the fraction of water vapor present in moist air. Okay? So dito guys, kino-consider natin the gas mixture ang air and water vapor. So we have two types, absolute humidity, where it calculates the mass of water per volume of moist air, and relative humidity, fraction of water vapor divided by the amount of saturation. So N actual, okay, yun yung most of your water vapor divided by N saturation. Okay? That is equal to P actual over P saturation. And in relation to that, relative humidity is just equal to the mole fraction of the water. Okay? Again, air and water considered as gas mixture times the total pressure divided by the pressure in as saturation occurs. Okay, so we will discuss more of that later. Now, watch this video, guys, to learn more about the Graham's law of diffusion. Okay, here we see that heavier, slower gas molecules, they will find a small hole less often. Okay, that's why larger and slower moving gas, they have slower effusion rates. And then lighter, faster gas molecules, o di ba, nawala na sila, lumabas na sila. Di ba? Kasi nahanap nila agad ang hole because they move faster, they move lighter, right? That's why smaller, faster moving gas, they have faster effusion. Cool, right? Ayan. And then this visualizes the Dalton's law of partial pressure. Here we see that the partial pressure of oxygen, nitrogen, argon, water, carbon dioxide, okay, makes up the pressure of air. Okay. So again, if you just sum up the partial pressures of these individual gases, we can get the pressure of your gas mixture, okay, which is air. Okay. Here ba, guys? And again, these are the equations. Okay. So the pressure of the ideal gas mixture is equal to the summation of the partial pressures of the individual gas components. Okay. I hope it's clear, guys. Okay. So tandaan nyo lang, nangyayari to kapag, for example, in a container, meron kayong more than one gas component. Okay? Tandaan, ang Dalton's law of partial pressures, guys, okay? Kasi lagi yan lumalabas. Never yan nawawala, okay? Ayan. Now, we have here relative humidity. Ang cute, di ba? Ayan, so these are the relative humidity equations, okay? So again, relative humidity, it is defined as the ratio of the actual partial pressure of water vapor in air. Again, partial pressure of water vapor pressure in air, P actual, divided by the saturation vapor pressure of water at the same temperature. Okay, so usually in percentage CRH. So guys, relative humidity, it tells us how full is the air of water. Punong-puno na ba ang air ng water? So for example, is the air 100% full, which is at saturation? Okay. Pag nasa in saturation na ang air mo, okay, meaning 100% full na siya of water, okay, it cannot hold any more water. That's why it is saturated of water, okay? Now, what about if your air is only 50% full and kaya pa niyang mag-hold ng more water? Okay? So that describes your relative humidity. I hope that's clear, guys. So parang tinitreat natin as container ang ating air. Tapos i-fill up natin yan ng water, di ba? Kita niyo dito, yung cloud dito, parang iiyak siya kasi punong-puno na siya ng tubig. Okay? So guys, that is what relative humidity is all about. And relative humidity, it changes as temperature changes. Okay? Guys, pag nagdi-decrease kasi ang temperature, okay? So yung container nyo is air, right? Yung container ng air, okay, it shrinks. So the amount of water it can hold, syempre, lumiliit din as you decrease the temperature. Okay? Dahil dito, yung air, which used to have a low relative humidity, can have a high relative humidity. Okay? Okay? So guys, pag sinabi natin na 100% yung relative humidity, that's another way to say that the air is at saturation or 100% full. Okay? So, kailan kaya guys nagiging at saturation ng ating air? That is when clouds form. Di ba? Pag nagpo-form tayo ng clouds, okay? Meaning yan, puno yan ng tubig, guys. Okay? Meaning yung air, puno ng tubig. Ayan. I hope it's clear, guys. Now, before we proceed in answering some sample problems relating to the gas laws, now let's describe the units of your gases. So, in terms of pressure, okay, 1 atm, atmosphere atm is equal to 760 mmHg. Okay? And that is equal to 760 torr and equal to 101.325 Pascal. Oh guys, SI units for pressure is Pascal. And that is equal to 1.01325 bar and equal to 14.7 PSI. Dapat memorize yan, okay? And then for volume, 1 liter is equal to 1 dm cube, and that is equal to 1,000 ml, and that is equal to 1,000 cm cube. So guys, 1,000 ml is just equal to 1,000 cubic centimeters. And temperature, okay, how do we convert Celsius to Kelvin? Just simply add 273.15. To convert Celsius to degrees Fahrenheit, simply multiply 1.8 plus 32. Again, degrees Celsius times 1.88 plus 32. And lastly, okay, for degrees R, that is equal to degrees Fahrenheit plus 459.67. Okay, tandaan yan. Again, degrees R, that is equal to degrees Fahrenheit plus 459.67. And for the universal gas constant, we can express this in 3 ways. So first, universal gas constant, that is equal to 8.314 J over mole K. So this is in terms of your SI units, and that is equal to 0.0821 LATM over mole K. And that is equal to 1.986 Cal over mole K. Guys, when you use these units, okay, make sure consistent. Okay, make sure consistent. Ayan. So let's try to solve this first sample problem. Propene and nitrogen fuse through a hole. If it takes 68.4 seconds for nitrogen to effuse, how long will it take for the hydrocarbon to effuse? So ang gagamitin natin equation ay the time it takes for gas B to effuse divided by the time it takes for gas A to effuse. And this is equal to the square root of the molar mass of B divided by the molar mass of A. So guys, ang ating TB ay ang time it takes for the hydrocarbon propene to effuse. So 68.4 seconds, that is the time it takes for nitrogen to effuse. So solving, get TB divided by 68.4 seconds, it is equal to square root of 42.08 grams per mole. So that is the molar mass of your propene divided by the molar mass of nitrogen, which is equal to 28.02 grams per mole. Solving, we get TB is equal to 83.8 seconds. Diba guys, we can easily just use the shift solve function in solving this problem, okay? Oh, so guys, ano masasabi natin dito, diba? Mas mabilis mag-effuse sino kaya guys? Tama, si nitrogen, right? It takes a shorter time for nitrogen to effuse, 68.4 seconds lang. Okay? Because it is lighter. Meanwhile, propene, it takes a longer time for propene to effuse, 83.8 seconds, because it is heavier. Okay? Next, let's answer the sample problem relating to the apparent molar mass concept. What is the apparent molar mass of air if its major components are nitrogen, oxygen, and argon? So the mole percentages are 78.10%, 20.94%, and 0.96% respectively. So let's solve. This is again your apparent molar mass equation. Solving, we get. So guys, again, yung Yi, yun yung mole fraction ng component mo. Treat nitrogen, oxygen, and argon as the gas components of the mixture, okay? Or the mixture of air. That was in 78.10, 20.94. These are your mole fractions. So 0.78, this is the mole fraction of your nitrogen times the molar mass of nitrogen, which is 28 grams per mole, plus, okay, the mole fraction of oxygen, 0.2094, times the molar mass of oxygen, 32 grams per mole, plus the mole fraction of your argon, that is 0.0096 times 40 grams per mole. Ma'am, bakit ka nag-divide by 2? Oh guys, tandaan, percentages to. Pag fraction, we have to convert the percentage to fraction. So solving, we get the apparent molar mass of air is equal to 28.92 grams per mole. I hope it's clear, guys. And then lastly, we have the sample problem on partial pressures or Dalton's law of partial pressures. What is the partial pressure of H2 in a gaseous mixture of He and H2 in a balloon? So dito, guys, okay, we have a mixture of two gases, He and H2, and its total pressure. So the total pressure of your mixture is 8.5 atmosphere. And ang number of moles ng H2 mo is equal to 0.5 moles. Total number of moles is equal to 1.75 moles. So we have to solve the partial pressure of H2, that is equal to the number of moles of H2, 0.5 moles, divided by the total number of moles. Okay, this will give us, guys, the mole fraction, right? This is your mole fraction. So YH2 times P total. So this is your total pressure for the gas mixture. Okay, so from there, let's solve the partial pressure. We get 0.5 divided by 1.75 times 0.5 atm, we get 2.46 atm. So this is the partial pressure of H2. Now, let's proceed to barometric distribution law. Okay, so here it explains how air pressure of air, and density, okay, decreases with height. Okay, so as you go up the atmosphere, guys, let's say nag-hiking kayo. Well, habang paakyat ng paakyat kayo, guys, the air gets thinner. Okay, that's because there is less amount of air above you. Now, what happens to the pressure? The pressure decreases. Okay, again, the pressure decreases because there is less air above you. Okay, so in simple terms, guys, the higher you go up a mountain, the less air there is. So yun yung kinakalculate natin sa barometric distribution law. So the final pressure at a certain height is pH or P here. Okay? P naught is your initial pressure. So kung galing ka dito, ito yung starting point ng height mo. Okay? Now, the equation has various forms. So P is equal to P naught. So P is after the pressure as the height. Pressure is the pressure given the height H. Okay? And P naught is the initial pressure times e to the power of negative mgz over RT. So M is your molar mass, G is your gravity, which is 9.8 kilogram times meter per second squared, and Z is your column height. So ito yung height, guys, si Z, okay? Divided by RT. And then we can also use it, concentration. So for example, we have an initial concentration C naught, the final concentration at a certain height Z, that is we can get the final concentration using this equation. C is equal to C naught times e to the power of negative mgz over RT. Lastly, we can get the density. So this is the initial density, is the final density at a certain height. So density is equal to initial density P naught is equal times e to the power of negative mgz over RT. Okay. And lastly, we can have a linearist form of our barometric distribution law. So that is ln P over P naught is equal to negative mg over RTZ, or ln C over C naught equal to negative mg RT over Z. So we can express this equation through this. Okay. So P naught mg over RTZ. Same then. Okay. Yeah, now let's move on to a sample problem to easily understand the barometric distribution law. So determine the final atmospheric pressure of argon with a molar mass of 39.95 grams per mole at 50 kilometers above sea level. So may given kayo na height, diba? Above sea level. Its initial pressure is 7.068 mmHg at 20 degrees Celsius. So guys, hanapin muna natin si negative mgz over RT. Okay. So as we solve, we get negative 39.95 times 10 to the power of negative 3. So guys, convert that into kilograms ang gram. Okay. To ensure that the value for negative mgz over RT is in SI units times gravity 9.8 kilogram times meter per second squared times the Z. This is your column height, guys. Column height. That is 50 times 10 to the power of 3 meters. So we convert kilometer to meters. Divided by the universal gas constant. So we use the specific constant para naka-SI units lahat. Okay? Times the temperature, which is also given. Solving, we get negative 8.036. Okay? And now we can solve for the final atmospheric pressure of argon. That is equal to P naught, which is 7.068 mmHg times e to the power of negative 8.036. Yan yung negative mgz over RT expression, right? Ito, and ito. Solving, we get 2.3 times 10 to the negative 3 mmHg. Okay, I hope that's clear, guys. Ayan. Now, let's proceed. Notice, guys, now, here, we cancel the units, right? Good. Again, let's proceed. Yeah. Now, the ideal gas law, it is a simple equation of state. Now, guys, when we say equation of state, it is a mathematical expression that relates to pressure, volume, temperature, and amount of gas. Again, it relates these variables. So, ideal gas law, it is a simple equation of state, or EOS, that describes the behavior of gases under conditions of high P and low P. Dapat memorize yan, guys, ha? Ideal gas conditions, high temperature, low pressures. Bakit? Because we are basing the ideal gases on the kinetic molecular theory. So meaning nito, guys, dapat yung volume ng gas particles and their intermolecular interactions are neglected. Okay? So the ideal gas law, PV is equal to nRT. Okay? We can express it in several forms. So this is the derived equations for the ideal gas law. Again, these are applicable to your ideal gases. So this is your original ideal gas law, and we can express it through molar mass, density, and concentration. First, for molar mass is equal to mRT over PV. Density is equal to PM over RT. So P is your pressure, capital M is the molar mass. And capital C is equal to P over RT. Okay? So guys, please feel free to use these equations depending kung anong hinihingi sa problem. Okay? Now, question. How was the ideal gas law derived? So guys, please watch this video to know how the ideal gas law was derived.
There are more sophisticated methods to derive the equation for the pressure of an ideal gas. But if you're looking for an easily understandable and straightforward derivation of the gas pressure equation using molecular kinetic theory, here it goes. Trapping a volume of gas inside of the container, the pressure inside is caused by individual particles colliding with the walls of the container. Let's zoom in on one single particle and isolate it from the rest of the gas. This particle collides into the wall with a momentum mu, where m is the mass of the particle and u is the velocity. Making the assumption that this collision is perfectly elastic, the particle will rebound with a momentum minus mu. They are the same magnitude, but the negative sign tells us that the particle is now traveling in the opposite direction. So the particle's change in momentum is the final momentum minus the initial momentum, giving us minus 2 mu. Do you remember the impulse equation relating the change in momentum and force? Force is equal to the change in momentum divided by the time of impact. Substituting this into the impulse equation, the force that the particle exerts on the wall is minus 2 mu over their contact time. But we are more interested in the force that the wall exerts on the particle. So according to Newton's third law, the wall exerts an equal but opposite force on the particle, which is just 2 mu over t, allowing us to drop the minus sign. I'm going to redraw this diagram so that we can see all the sides of the container with the 3 dimensions x, y, z. We're now going to utilize the most basic equation, speed is distance over time. The time it takes for this particle to make it from this side of the container to this end, and then back, is 2x over the speed of the particle. Plug this back into the impulse equation. We get the force exerted by one particle to be this. But by definition, pressure is force over area. The cross-sectional area of this container is y times z. But the volume of this whole container of gas is equal to xyz. The equation for pressure now reduces to the mass times by the speed squared divided by volume. This is beginning to look a lot like the kinetic theory equation that we're trying to derive. But where has the factor of a third come from? Well, pressure is a scalar quantity that acts in all directions. The increase in pressure caused by each collision will on average be distributed evenly in each of the x, y, and z axes. So we need to divide the right-hand side of the equation by 3 to take this into account. But this is pressure due to just one single molecule of gas. If we have n number of molecules in the gas, we have to multiply by n. We're almost there now. All that's left is the subscript RMS, which stands for root mean square. To find the root mean square of a set of data, we need to square each number, add them up, divide by the number of data points there are, and finally take the square roots of everything. This is a mathematical method used to find the average speed of the molecules in a gas. Since there are n number of molecules in our volume of gas, to find the root mean square speed, we have to square the different speeds of the individual molecules, add them together, and divide by n before square rooting everything. So here we have the final form of the equation for gas pressure derived using the concepts of molecular kinetic theory. Thanks for watching this video on molecular kinetic theory. Be sure to subscribe for more physics.
Ayan. So now we know how we can derive the ideal gas law. Okay. So guys, this is just a supplemental information. Okay. It just tells us how we can determine the ideal gas law. Okay. Ayan. So no need to memorize the derivation, guys. Okay. So now let's proceed. Okay. So here in this figure, okay, we see the movement of ideal gas. Okay. Ayan. Okay. Again, the ideal gas law relates to macroscopic properties of ideal gases. So an ideal gas is a gas in which the particles, number one, do not attract or repel one another, as you can see here. Okay? And two, they take up no space, meaning they have no volume. That's why volume is negligible for ideal gases. Okay? Note, guys, that no gas is truly ideal, but the ideal gas law provides a good approximation of real gas behavior under many conditions. Okay? So, tandaan nyo guys, pag ideal gas, theoretical gas siya, made up of particles that move in straight lines, don't attract or repel each other, and take up no space. Okay? Now, guys, with that, let's solve some ideal gas problems. Okay? Using the following data for a sulfur sample behaving as an ideal gas, determine the identity of the given allotrope. Ayan, so we are given the density 3.71 grams per liter, temperature 773 Kelvin, and pressure 699 torr. So guys, ano kayang pwede natin gamitin na equation? It is the density equation. Density is equal to Pm over RT. So simply substituting, we can get M, the molar mass, is equal to PRT over P. Okay? Substituting 3.71 grams per liter, your density, times 8.0821 atm over mol K, times 773 Kelvin. Divided by the pressure, 699 torr. Let's convert it to atmosphere, where 1 atmosphere is equal to 760 torr. Oh, ma'am, bakit in terms of 0.0821 ang gamit kong R? It's to cancel the units, guys. Okay, again, we have to cancel the units. We have to be consistent with our units. So for our density, the unit is grams per liter. May liter tayo. So para hindi ko na i-convert sa liter to its SI units, gagamitin ko na lang ang universal gas constant na 0.0821 because it has an expression, a unit for liter. Okay? And then, since your universal gas constant has a unit ATM, edi ko-convert natin si torr to ATM. So that we can cancel the ATM. Okay? Cancel, cancel, cancel. Tapos, cancel, cancel. Ang natira na lang ay si grams per mole, which is the units for your molar mass. So molar mass is equal to 256 grams per mole, and this is equivalent to the allotrope of sulfur. Ma'am, ano nangyari? So, guys, tandaan si sulfur, its molar mass is 32 grams per mole. To get the allotrope, simply divide the calculated molar mass to the molar mass of sulfur, and we get 256 divided by 32. The allotrope has 8 sulfur atoms. So yung identity ng ating allotrope ay S8. Diba? Because ang molar mass ng S8 ay 256 grams per mole. Okay? Hope it's clear, guys. And then lastly, let's answer this. What are the partial pressures of 1 gram of oxygen and 1 gram of hydrogen at 27 degrees Celsius and occupying a 2.0 dm cube container? So we will use the ideal gas law in solving this. Okay? Substituting, we get the partial pressure of oxygen. We get 0.03125. So guys, ang galing yung 0.3125. So that is from, okay, converting this to moles, right? So 1 gram, we will get the number of moles for oxygen. That is 2. This equation again, mole 2 divided by, oh guys, ano yung molar mass ng ating oxygen? Tama, it is 16. It is 32, right? Ayan. So cancel the grams, we get the moles of O2. Diba? 1 divided by 32, we get, yes, 0.03125 moles times R 0.0821 times the Kelvin 300.15 divided by 2 dm cube. Tandaan guys, si dm cube, that's just equal to liter. Okay? That's why, ang ginamit natin R dito is si 0.0821. Solving, we get 0.3845 atmosphere. And lastly, if we get the partial pressure of hydrogen, we get this equation, 0.496. So this is the number of moles for H2. Okay? So we simply just converted 1 grams of H2 to moles. Okay? 0.496 moles times 0.0821 times 300.15. We get, divided by 2 dm cube, we get 6.12 atmosphere. Okay? Ayan. So let's proceed to the next part of our discussion, and that is for real gases. Okay? So, guys, we have here ideal gases. Here, we assume that IMFAs are negligible. However, for real gases, guys, there are attractive forces between gas particles. Okay, so what describes real gases? Okay, so these are the features of real gases. First, they have significant interactions between molecules. So dito, guys, tinitake into account na natin yung interactions ng mga gas molecules. Specifically, they have attractive forces that we take into account. And of course, now we don't neglect the volume because we have an appreciable volume of molecules. Okay? And the collisions, they are not perfectly elastic. Okay? Meaning, meron tayong net energy lost or gained as the gas molecules collide. Okay? And tandaan to guys, ang real gas, they have high P, low temperature conditions. So kanina sa ideal gas, meron siyang low P, high T conditions. Si real gas naman may high pressure and low temperature conditions. And lastly, real gases can be liquefied. Okay? Meaning, kaya natin silang i-convert into liquid because of the interactions between molecules. Okay? So that is the behavior of real gases. So ideal gases, guys, they cannot be liquefied, diba? Because we neglect the interaction of molecules. Okay? Ideal gases, they have elastic collisions. So real gas are opposites of ideal gases. Okay? So in this chapter of our crash course, we will define real gases and how we can account for the deviation from ideal behavior. Diba? Kasi guys, if you want to calculate various parameters of real gases, we have to take into account the deviation from ideal behavior. And this is through the modified equation of state, compressibility factor, fugacity coefficient, and Joule-Thomson coefficient. And so first, the modified equations of state take into account the deviation from ideal behavior in real gases. Guys, pag sinabi kong real gases, an example ito, si oxygen, it is a real gas. Nitrogen, it is a real gas. Okay? Now, in the modified equations of state, tinitake into account natin ang strength ng intermolecular attractive forces, A, with the variable A, and finite molecular size of gas particles or their excluded volume, B. Because we have significant interactions between gas particles and significant volumes of particles. So table 21 shows the equations of state for real gases and their parameters. So dito guys, yung A na pinapakita and yung B. Okay? A refers to the intermolecular attractive forces. So yung expression na to takes into account yung IMFAs. Okay? And then si B naman takes into account the finite molecular size of gas particles and the excluded volume. So it is expressed by this equation. Okay? So we have many types of equations of state, and these are, first, van der Waals. This equation corrects the ideal gas law by accounting for intermolecular attractions with A, so yun, and finite molecular volume using B. So it is one of the earliest attempts to model real gases more accurately. So guys, diba, we had the ideal gas equation of state. So si van der Waals, okay, this is applicable to real gases. Okay? Again, it takes into account the IMFAs and the excluded volume of your particles. Okay? So again, it takes into account A and B. So here the equation is P is equal to nRT over V minus B minus N squared A over V squared. Yan. Okay? Dapat memorize si van der Waals equation of state, okay? Because ito yung pinaka-common na equation of state for real gases. And then for the rest, guys, okay, you don't have to memorize it, but you have to understand how these equations differentiate from van der Waals, okay? So for the Berthelot equation, it improves upon van der Waals. So si van der Waals, in-improve pa siya lalo by making the attraction parameter temperature dependent. So di ba guys, si A, okay, it accounts for the intermolecular attractive forces. Now, ginawa nilang temperature dependent ang attractive forces na expression. Okay? Because molecular interactions, di ba? At higher temperatures, di ba, mas bumibilis ang speed ng molecules, mas nag-interact ang mga molecules, di ba? That's why we take into account the temperature here. Kita nyo guys, when we get to Berthelot, meron na tayong temperature dito. Okay, van der Waals, wala. Okay? Take note that, guys. And then for Redlich-Kwong, it refines gas behavior further with a better treatment of temperature effects on attraction forces. So, mas in-improve lang ng Redlich-Kwong ang equation of state for real gases, okay, by offering improved accuracy at moderate pressures and temperatures. So, same as Berthelot, it also assumed that intermolecular forces are temperature dependent. Pero in-improve lang niya further ang ating equation in a way that it can be used in real gases with moderate pressures and moderate temperatures. Okay? And then we have Dioterici. So Dioterici naman is also another improvement of your equation of state for real gases. Here, an exponential term is introduced, right? Ito. So tandaan niyo pag may Dioterici, may exponential term yan, okay? To model how attraction affects pressure more smoothly. So diba, ito yung attraction mo na expression si A. Okay? So it shows us how attraction affects pressure more smoothly, especially near the critical point. And lastly, the virial equation. Okay? So guys, the virial equation kailangan i-memorize. Okay? It is just a series expansion used to describe your real gases, okay? Where the coefficients B, C, etc., they represent molecular interactions. So ginagamit ito mostly for low density gases. Okay? Yan. Now, specifically for the van der Waals equation of state, okay? Again, the equation is most accurate to spherical gas molecules. Tandaan to, ha? Applicable to spherical gas molecules with near ideal behavior and weak London dispersion forces. For example, sky neon, helium, methane, and carbon tetrafluoride. Okay? So here is the equation for our van der Waals equation of state. Again, this expression here, N squared A over V squared, it accounts for the pressure decrease due to the intermolecular attractive forces between molecules. So guys, diba? Again, we now take into account the IMFAs between molecules. So when they interact, guys, pag nag-attack sila with each other, the pressure decreases. Okay? Kasi hindi na sila nag-move in random motion. Rather, nag-interact na ang molecules mo with each other. That's why the pressure decreases. And then the V minus B here, okay? It accounts for the volume available for molecular motion. Okay, and then guys, here in real gases, we take into account the volume of gas particles, right? So we have to take into account in the equation the volume available for molecular motion. Meaning, saang volume, guys, pwede gumalaw-galaw ang ating gas particles. Where NB refers to the total volume of the molecules. Okay? So guys, yung NB, to take into account natin, yung total volume ng gas molecules mo. Tapos, subtract NB from V. And then this equation here, V minus NB, will give us the total volume available, the net volume available for the gas particles to move around. Okay? I hope that's clear, guys. Now let's try to answer the sample problem on van der Waals equation of state. Calculate the pressure exerted by 25 grams argon in a 1.5 vessel at 30 degrees Celsius if it behaves as a van der Waals gas. So we are given the values of A and B. Okay? So we simply just have to substitute. So our van der Waals equation of state is P is equal to nRT over V minus NB minus N squared A over V squared. Substituting, we get first the number of moles. So how do we get the number of moles? Through the mass of argon. So number of moles of argon is equal to 25 grams times the molar mass of argon, 1 mole over 39.95 grams. We get 0.6258 moles of argon. Solving for the pressure, this is N, 0.6258 mole, times R, 0.0821 LATM over mole K. O bakit natin ginamit si 0.0821? Because the units of our A and B, diba, naka LATM, L mole. So, to easily cancel out the units, we use this universal gas constant times 303K, so this is your temperature, divided by 1.5. Okay? So ito yung general volume ng vessel mo kung saan makikita mo yung gas particles. And then minus NB, so this is your NB. Okay? Now, this takes into account the total volume of your gas molecules. So, hanapin natin, guys, yung volume ng gas molecules mo itself. Okay? So, here we have 0.6258 moles N times B. Again, B takes into account the finite molecular size or the excluded volume of every gas particle. So, that's times 3.2 times 10 to the negative 2 L per mole. Minus N squared A over V squared. So, N mo ito. Ang A mo ay, say, 1.337 L squared ATM over mole squared ito. Okay? Divided by the volume, 1.5 squared. Solving, we get 10.3 ATM. Diba? Kayang-kaya? Okay, now let's proceed. Now, we also have what we call critical parameters. Now, critical parameters, guys, okay, it takes into account the critical temperature, critical pressure, and critical volume. Okay? This is what we call the critical parameters. So, tandaan niyo, guys, pag real gas, meron silang critical parameters ng mga ito. Okay? So, when we say critical temperature, it is the temperature above which a gas cannot be liquefied. Again, at the temperature at which the gas cannot be liquefied. Okay? No matter how much pressure ang i-apply natin. And then critical pressure naman, it is the minimum pressure we need to liquefy a gas at its critical temperature. And lastly, critical volume, it is the volume occupied by 1 mole of a substance at the critical point. Again, volume occupied by 1 mole of a substance at the critical point. Okay? Guys, ano ang relevance ng critical point? At the critical point, the gas and liquid, again, they become what? Indistinguishable. Hindi mo na sila ma-differentiate from one another at the critical point, above the critical point. Okay? Now, that's where the ideal gas laws break down completely. Okay? And again, this is the critical parameters. This is the condition. So how can we get the critical point? Through these equations. We have to find the first and second derivatives of P with respect to V to 0, equal to 0. Okay? And then for the principle of corresponding states naman, okay, it just says that all gases, okay, pag compare natin sila at the same reduced temperature, PR, okay, reduced pressure, PR, and reduced volume, VR, okay, then those gases, they behave similarly due to the principle of corresponding states, okay? So, para siyang universal rule, guys, okay? If, for example, you have two different gases, pero nasa same reduced condition sila, then they will show similar deviations from ideal behavior. Pareha sila ng deviations from the ideal gas behavior. Okay? So, tandaan ha, pag corresponding states, they let us compare all gases on a same level playing field, diba? Kasi same sila ng reduced conditions. Okay? So, ang equation ay P is equal to PR, your reduced pressure, times the pressure at the critical point. And the temperature is equal to the reduced temperature times the temperature at the critical point. And volume is equal to the reduced volume times the critical volume. Okay? Yan. Now, another factor which takes into account the deviation from ideality is the compressibility factor. So it describes the ability of a gas to be compressed at a certain condition and the extent of deviation from ideal behavior. Okay? So the equation is compressibility factor Z is equal to V actual, the volume of the actual gas, divided by the volume of the ideal gas, or the ideal volume. And this is equivalent to PV actual over RT. For the truncated form, guys, okay, we can use this if we have a given B, which is the excluded volume, and A, finite molecular size. So Z is equal to 1 plus BP over RT minus AP over RT squared. Now, guys, if Z is equals to 1, then meaning yan, our gas is ideal, and it has an ideal gas behavior. So here, guys, example yan is if V actual is the same as your V ideal. And then next, if you have Z is greater than 1, then your actual volume will be different, right, from your ideal volume. That's why you will have a real gas that is harder to compress. So when Z is greater than 1, then assuming that ideal volume is still the same, okay, V actual is greater, right? It is greater, meaning it is harder to compress because of the repulsive interactions between the gas molecules. So guys, when the gas molecules, they repel each other, then the volume of your gas will expand. Okay, that's why Z is greater than 1. Next, Z is less than 1. This also results in a real gas. Okay, and it means that the gas is easy to compress because of the attractive interactions between the gas molecules. So for example, if Z is less than 1 and V ideal is still the same, then V actual should be lower, smaller, right? V actual should be very small, so that Z will be less than 1. Now, V actual will become very small. You will have a small volume when there are attractive interactions between molecules. What will happen is that the gas molecules, they will interact with each other, okay? And that will shrink, that will compress the volume of your gas, okay? So guys, bakit if Z is greater than 1, that results in the deviation from ideality. So that is because of the significant contribution of the molecule's volume, okay, to the total gas volume, okay? Since malaki yung mga molecules nyo, it also has a big contribution to the total gas volume. Kaya malaki sila, it is easy for them to be repulsive with each other. Tapos, if Z is less than 1, it also deviates from ideality because there is an increasing IMFA strength. So guys, if we have an increased IMFA strength between gas molecules, then it is harder to break those intermolecular forces. Okay? That's why nagko-compress ang volume mo. Or we have a shrink volume for your real gas. Okay? So this graph, guys, describes what happens if Z is greater than 1 and Z is less than 1. Again, Z is greater than 1 is due to the increasing IMFA strength. Z is less than 1, okay, because of the gas's volume, which is because of the gas molecule's volume, which contributes to the total gas volume, which increases V actual. Kaya V is greater than 1 in that case, okay? So for example, guys, okay, this is your ideal gas line. Yeah? Z is equal to 1. As we deviate from ideality, yung real gas, meron silang Z is greater than 1. For example, CN2, CH2, HE, okay? CO2, then it is a real gas. Therefore, it deviates from ideal behavior. That's why it's Z, it's not equal to 1. Okay? I hope that's clear, guys. Again, tandaan ang equation for Z, that is equal to PV actual over nRT. Okay? Okay. Now, we have the boil temperature. So the boil temperature is the temperature at which the real gas becomes ideal, or Z is equal to 1. Okay, again, boil temperature, it is the temperature at which the real gas becomes ideal. Okay? So merong point at which the real gas can become ideal, or Z is equal to 1. Okay? Specifically, guys, at the boil temperature, the second virial coefficient, okay, so ito, okay, yung B niyan, that will be equal to 0, okay, indicating that the attractive and repulsive forces between the molecules are now balanced. Again, if B is equal to 0, meaning yung attractive and repulsive forces ng mga molecules are balanced. Okay? Yan. So, dahil dito, what will happen to Z? The Z will approach 1 over a wider range of pressures, okay, which indicates that the gas will also approach ideal behavior. Okay. Now, fugacity coefficient also takes into account the deviation from ideality. So the fugacity coefficient is the ratio between fugacity and pressure. Okay? Fugacity, yun yung effective or actual pressure. It arises from the attractive and repulsive forces between real gas molecules. So how do we calculate for fugacity coefficient? Okay? Fugacity coefficient is equal to F over P. So F is your effective or actual pressure. P is your pressure for the gas. Okay? That is equal to E to the power of the integral of Z minus 1 over P dP. From P star, the pressure at C is equal to 1, or the ideal pressure, to P. Okay? So P dito, guys, yung walang star, that is for the real gas. Yung P star, that is the pressure at Z is equal to 1, where the gas is behaving ideally. Okay? So guys, meaning nito, if we use this equation, we have to calculate for the compressibility factor first before we can calculate for the fugacity coefficient. Okay? So this table shows the relationship between the F and P. So if the dominating force between gas molecules are attractive forces, okay, so the effective actual pressure is less than the P, right? Again, it is less than the P because we have attractive forces that allows the interaction of the molecules. And with that, if we calculate the fugacity coefficient, it will be less than 1. And then for repulsive forces between gas molecules, the effective or actual pressure will now be greater than the pressure of the real gas. Diba? So here, the fugacity coefficient will be now greater than 1. So the Joule-Thomson coefficient, mu JT, again, diba na-discuss natin ito sa thermodynamics 1? It indicates a change in temperature upon the change in pressure of a real gas at constant enthalpy. So this occurs for an insentalpic change or insentalpic expansion because the enthalpy is constant. Okay? For an ideal gas, mu JT is equal to 0, right? Because it cannot warm nor cool during throttling in the Joule-Thomson apparatus. Okay? So, guys, what is throttling? So, gas. So, kunwari, meron tayong gas. Papasok siya sa isang porous plug. Kunwari dito. Okay? So, yung gas, pag magpapass through siya dyan, it does not do any work, walang heat exchange. Okay? Yung movement niya dyan is called the throttling process. Okay? Meaning, when it's there, we can calculate its pressure or its change in temperature as we change the pressure. Okay? Clear, guys? Now, during throttling, diba? Some gases, they cool down. Some gases, they heat up. Yun yung tinatawag na Joule-Thomson effect as we discussed earlier. Okay? Note guys that the Joule-Thomson coefficient, it depends on the initial temperature and type of gas. Okay? So, guys, actually, most gases, kagaya ng carbon dioxide and nitrogen gas, at room temp, they can actually cool when they expand through a valve. So, for example, nasa porous plug sila, okay? Yung CO2 and N2 mo, they will cool as they expand or as you decrease the pressure. Diba? Pag nagde-decrease tayo ng pressure, nung nangyari, syempre, nag-expand din ng volume. So, ang effect nun kay carbon dioxide and N2 ay it cools. These gases cool or nagde-decrease ang temperature nila. Okay? So, the equations for the Joule-Thomson coefficient is UJT is equal to TPH, as we know earlier. And if we derive this, we get negative HPT times THP. And then another term for the Joule-Thomson coefficient is T times VTP minus V over CP. So, how do we derive this? So, for the equation on the left earlier, okay, diba, the general equation is mu JT is equal to TPH because it involves the change in temperature as we change the pressure at constant enthalpy. So we can just use the chain rule identity to determine this equation. So TPH is just equal to negative HPT times THP. So guys, again, we just use a chain rule identity. Okay? Now here, okay, so kaya yan guys, step-by-step lang. So for the derivation of our Joule-Thomson coefficient, first we start with our enthalpy equation. This is H is equal to U plus PV. Okay. Now, if we get the total differential of H at constant pressure, we get this equation. dH is equal to TdS plus VTP. If you divide both sides with change in P, ito, okay, we get HPT. Bakit may T? Because we divide both sides by P at constant T. So HPT is equal to T times change in entropy divided by P at constant T plus V. Ba? Now, remember Maxwell relations from thermodynamics too? So we can actually use this in determining another expression for the partial derivative SPT. So SPT is just equal to negative VTP based on our Maxwell relation square or Vatov shape, okay? And substituting, we get HPT is equal to negative T, VTP plus V. Now, we can now substitute the HPT expression here, dito, to the Joule-Thomson coefficient equation. Diba? Ito yun. Ito yun, guys. Wait lang. Ito. So, yung HPT na nakuha natin, okay, yung HPT, isa-substitute natin sa equation na to. So, let's do that. Ayan. So, mu JT is equal to negative times negative T, VTP, plus V. Observe that, times THP. Now, okay, you all know that CP is just equal to HTP, right? So, okay, we can just get the value of 1 over CP. Substituting, we get mu JT is equal to T, VTP, minus V divided by CP. Diba? Kaya-kaya yan. So, ganun mag-derive ng Joule-Thomson coefficient. Okay? Okay. Again, rate of temperature change. Ito lang yun, diba? Based on our discussion sa crash course ng thermodynamics 2. But again, the temperature at which the mu JT shift sign is what we call the inversion temperature. Again, inversion temperature is equal to 2A over RB. Again, it is the temperature at which our real gas changes behavior in terms of heating or cooling when we allow it to expand or when we decrease the pressure. Okay? So again, guys, nangyayari sa throttling process, ba? Naglalagay ka ng gas sa porous plug and then you change the pressure by decreasing it. Okay? So, aalamin mo kung whether or not the gas will heat or cool upon expansion, upon the lowering of pressure. Okay? Yun yung throttling. Okay? So guys, ang meaning lang ng TI is equal to 2A over RB is that if you have a large A, which accounts the IMFA strength, then meaning you have stronger intermolecular forces, right? If this is large. Okay? And that results in a higher inversion temperature because this is high. Okay? Meaning the gas will cool upon expansion. Okay? Even at higher temperatures. Okay? Next, a larger B, which means larger particle size. Okay? So meaning malaki yung particle size, ano mangyayari kay TI? Okay? This results in the lower inversion temperature. Okay? So, these a lower temperature in order to shift sign. Okay? Ayan. So now, let's proceed to table 8. Ayan. So again, this is just a review of what we have learned in thermodynamics 1, right? Thermodynamics 1. So again, if mu JT is greater than 0, meaning gas cools upon expansion. Ang condition ay lower P and lower T. Diba? Because, tandaan, in a throttling process in Joule-Thomson, we decrease the pressure in order for the gas to expand. And if mu JT is greater than 0, then meaning gas cools upon expansion. Next, if mu JT is less than 0, gas warms upon expansion. So, ang conditions niyan ay low pressure and higher temperatures. And lastly, if mu JT is equal to 0, then meaning there is no temperature change upon expansion. Thus, as we decrease the pressure, there is no change in T. Now, guys, we can use the compressibility factor, fugacity coefficient, and the Joule-Thomson coefficient to summarize the behavior of your ideal gas. So, table 23 shows the indicators of deviation from ideal gas behavior. So, guys, if we have attractive forces between your gas molecules, then the volume will compress. The range is relatively long, meaning meron tayong van der Waals attractions between the molecules. And the van der Waals attraction, guys, these can act over large distances, meaning kahit malayo ang mga gas molecules from each other, they can still have attractive forces. That's why the range is relatively long. So, if the Z is less than 1, and fugacity coefficient is also less than 1, then mu JT is greater than 0. Okay, guys, so please correct this in your manuals. Table 23, mu JT must be greater than 0 for attractive dominating forces. So this is seen at low temperatures and low temperatures and low pressures. And then next we have for repulsive dominating forces, the effect on volume is expansion. This range is short. Because for example, the molecules, they are very close together. Habang nagko-collide sila, the molecules will push each other away because they're too close with each other. That's why the gas will resist compression, and therefore the gas will expand its volume. So it is dominant naman at high pressures and high temperatures. So Z must be greater than 1, fugacity coefficient must be greater than 1, and mu JT, the Joule-Thomson coefficient, must be less than 0. So ano meaning yan, guys, pag mu JT is greater than 0, diba? Gas cools upon expansion. Pero pag mu JT is less than 0, gas warms upon expansion. Lastly, for non-meaning yan, guys, diba, for ideal gases, we don't have dominating IMFAs. Wala tayong IMFAs because these are negligible. So there's no effect on the volume. That's why Z is equals to 1, fugacity coefficient is equal to 1, and mu JT is just equal to 0. So again, kindly correct the table on page P35. Thank you. So now let's answer the sample problem. Consider a sample of H2 gas with a volume of 5.0 dm3 mole, pressure of 5.3 atmosphere, and temperature of 298 Kelvin. Determine whether the gas is experiencing expansion or compression, assess its tendency to escape, and predict whether it will warm up or cool upon expansion. So guys, when I say assess the tendency to escape, we have to get the fugacity coefficient. Because guys, the fugacity tells us the tendency to escape, or the tendency for the gas molecule to escape. So guys, kung makalimutan nyo man, ang definition ng fugacity, tandaan nyo lang, ang root word niya. Ano bang root word niya? Fugitive. Diba? Mga fugitive, lumalabas sa kulungan. So ganun din ang fugacity. Diba? They have a tendency to escape. Fugacity, fugitive. Now, first, let's solve for the compressibility factors. That is Z is equal to PV over RT. Substituting, we get 5.3 atm, that is your pressure, times 5 liters of hydrogen, which was given also. So guys, tandaan ha, pag dm cube, liters yan. Again, liters yan. Divided by 0.0821 LATM over mole K. So this is your universal gas constant. Again, ginamit ko yan in order to cancel the ATM units and the L units. Lastly, 298K ang temperature. Since Z is equal to 1.08, right? This is greater than 1. Thus, the gas will undergo expansion. Diba? Since Z is greater than 1, meaning the gas undergoes expansion. Next, we go to fugacity coefficient. Again, it is a tendency to escape. Let's solve. So E is e to the power of the integral of 1.08 minus 1, Z minus 1, divided by 5.3 ATM dP from 1 ATM to 5.3 ATM. Diba? Kasi yung 5.3 na yan yung pressure ng real gas mo. 1 ATM is our pressure for our ideal gas, or Z is equals to 1. Solving, we get 1.07 ang ating fugacity coefficient, which is greater than 1, meaning the gas has a tendency to escape. And lastly, we have the Joule-Thomson coefficient. Since Z is greater than 1 and fugacity is greater than 1, then mu JT is less than 0. So the gas warms upon expansion. So H2 gas warms upon expansion. Ayan. So ganun magsagot, guys, di ba? Kayang-kaya niya yan. Very straightforward, okay? So in general, these are the equations that we used earlier. So for ideal gas equations, ito yun. And then this also for the ideal gas equations. And lastly, these were the equations used in the real gas equations. Note, guys, that we don't have to memorize Berthelot, Redlich-Kwong, Guttili, and Virial. Okay? You can memorize Virial. And of course, van der Waals equation. Pero yung others, guys, basta gets yung concept, carry na yan, okay? And now, ayan, patapos tayo, Pasko na, guys, okay? Let's proceed to our Chloe cards. Answer with me, okay? It consists of postulates and assumptions that explain the behavior of gases, kinetic molecular theory. The velocity at which the largest amount of gaseous molecules are moving. Okay, so that is your most probable velocity. Di ba sabi ko kanina, siya yung may smallest na velocity. Okay? Siya yung pinakamabagal. Diba? Meaning, it has the largest amount of gaseous molecules moving. Kasi you would need a large mass of molecules in order to have the lowest velocity. Okay. Next, it describes the movement of gas particles through a small hole, Graham's law of diffusion. Next, it describes the behavior of gases under conditions of high temp and low P. Ano yan? Ideal gas law. Lastly, this equation is most accurate to spherical gas molecules with near ideal behavior and weak London dispersion forces or van der Waals interactions. Tama, it is van der Waals equation of state. And congratulations, guys, we are done with Crash Course 5. Okay, so now you may answer practice test 4 for 25 minutes. Yeah. And then after which, you may now proceed in watching your Crash Course 6, the liquid state. Go, guys.